Thank you all for coming. We're happy to have Djordje Radicevic here from Fermionic Institute telling us about how to better define entanglement entropy. Thanks.
Thanks, Dan. Thanks everyone for having me here. It's nice to be here. This is my first visit to Texas A&M, my first visit to Texas, period. So far, so good. I'm going to talk about some very simple things concerning the notion of entanglement entropy. This talk is based on a recent paper that I wrote with Jennifer Lin. And in it, we sort of crystallized some lessons that have been learned over the last 20 years of trying to compute entanglement entropy in various theories. So a lot of the talk will be elementary, but it's inspired by pretty subtle phenomena. And the lessons will be, I think, interesting. And everything will really concern how the question of how to properly define entanglement entropy to do what was, originally intended to do, but to also make sense in as broad an array of theories as possible. So let us start. Can I use this?
Yeah, it should work just fine.
Okay. Okay. So let me first give a short sort of historical introduction. Like this is a line here, which has been which pretty much appears in every paper that talks about entanglement entropy in QFT or in condensed matter systems, and it essentially goes like this: the original story. Entanglement entropy is some number that serves to quantify the amount of entanglement between degrees of freedom in some spatial subregion with the rest of your system. And the way you get this number is you follow this algorithm. So first you compute what's known as a reduced density matrix. So you start from a given state. You trace out all the degrees of freedom that are outside of the region of interest. You get an object called the reduced density matrix, and then you form this combination out of it and take a trace over the remaining degrees of freedom. This gives the von Neumann entropy of the reduced density matrix, and this is a number which is positive and can in general be anything in between 0 and the logarithm of the dimension of the Hilbert space of this in this reduced region. And of course, if you're talking about a quantum field theory in a continuum, this can be any positive real number. And of course, because we're calculating something that's defined on an interval with sharp boundaries, this is actually going to be a quantity that's sensitive to arbitrarily high energy physics, because you probe things that are happening arbitrarily close to your boundary. So generically, in a quantum field theory, or in any normal, even in any normal kind of lattice theory that we care about, this will diverge as we go to the thermodynamic limit, as we take the lattice spacing to 0. And we always need to see what happens as we take a regulator to be small enough. But nevertheless, many interesting phenomena, many interesting things can be computed. Universal quantities can be extracted from this number, and they tell us interesting things about the field theory in question. And I'll mention some of them later. Good. So this is a nice thing to compute. It can be computed in many ways, even holographically. But what I want to talk about today has nothing to do with UV divergences. Or at least that is not a problem that I want to try to address. I mean, we know how to address it. You just regulate, and we know what universal terms we kind of expect to get. In fact, the problems that I want to discuss today are issues that really exist even if there are no UV divergences in this calculation. Even if we are talking about a completely finite system, let's say a theory on a finite lattice, with a finite dimensional Hilbert space, things that people like to study in many body physics. And there are several issues with this definition even there. The most notorious issue concerns this first question that I've written there. So how do you apply this if the Hilbert space does not factorize nicely into something that's inside and outside of your region? You can't really. You have to supplement this rule with some extra guidelines, let's say, extra prescriptions. And over the last 5 to 10 years, people have come up with many ways to do this. They all give sensible results, and they're all morally equivalent to what I'm going to talk about today. This is fairly well understood. But nevertheless, it's important to already realize that let's say in a gauge theory, or in any theory where we have a global constraint that we want to impose, this is already not good enough. Now, another issue, which is slightly less notorious, but also quite confusing to many people who think about this, is that entanglement entropy does not seem to map nicely under dualities. There are a few examples where you have enough power to compute it on both sides, both in a strong and weak coupling side of a duality, let's say. And there, it can easily turn out that the entropies do not match on the two sides. So that's puzzling. The stuff that I'm going to be talking about in the rest of the talk will address that. But I actually have an earlier paper which is precisely devoted to that, so I will not go into huge details on this duality story now. But you're welcome to ask me later or offline if you were interested in the details of that. And then a third issue that is not really appreciated, but is still an issue, is the following. If you care about a fermionic theory, or a theory where particles have some exotic, even more exotic statistics, then to define a Hilbert space, you need to specify some ordering of the creation operators. And you need to understand how does this definition make sense if you have different as you change the ordering, or does it depend on the ordering or not? So basically, how to deal with graded Hilbert spaces, not ordinary Hilbert spaces. I will also remark on how this is addressed in the middle of the talk. So these are things that are necessary to understand better. And as I said, we know how to do this. This is not new in this particular paper I'm talking about. This has been known for, let's say, 5 years. And really the idea is to start from a concept that was known to quantum information theorists for many, many years, which is to, instead of talking about an entropy associated to a region, start talking about an entropy associated to an algebra of observables, an algebra of operators, rather. So you can always take a bunch of operators that all happen to live in the same region, ask for their algebra, and then say, okay, well, this is the algebra of that region. This is the entropy that I can associate to that region. And let me just quickly remind you one fact about algebras that's going to be useful. And it's written here. So algebras are essentially vector spaces, which also have a notion of multiplication in them. And the best example to keep in mind for the rest of the talk is that of complex matrices of a fixed size D. They obviously have matrix multiplication, and they form an algebra which is D squared, which has D squared complex dimensions. That's just the algebra of D by D complex matrices. And essentially, you can think of them as operators, as all the possible operators that connect on a D-dimensional Hilbert space. And pretty much everything we say is going to, we can think about all the operators as matrices on a Hilbert space which has some very large dimension. Good. And the procedure for calculating an entropy of a given algebra it goes as follows. So you have to pick an algebra which is nice enough. You pick a unital star algebra. It just means it contains the identity matrix, and it means it's closed under Hermitian conjugation. You take an algebra like that. Let's say you pick the algebra that contains only operators that are supported in some spatial region. And you have, of course, some starting state rho. And then you can define the unique reduced density matrix, which I call rho v, via this system of equations. So you write an equation like this for each operator in your algebra. By linearity, you really need to write it for every basis element of your algebra. Yes?
So are you assuming that D is finite?
Yes. So morally, as I said, you want to think about everything as being finite, but then taking D to infinity will make sense here. So I will only talk about I will only assume that I'm talking about theories where I know how to take D to infinity. I don't want to start with let's say an algebraically defined QFT where everything is already in the continuum and where I don't have any regulator. I want to start with a regulator and just take that regulator to be, large in this case. So I want to have a well-controlled limit.
V is still a region?
Yeah, that's right. And of course, depending on what exactly degrees of freedom I have, these degrees of freedom can live on links or sides of a lattice or something like that. But for now, it's completely general. It's some rule that says pick a subset of operators.
For the examples you get, will it be clear that the set of operators is in some sense complete?
Let's see, what do you mean by complete?
Well, I just mean that they, that you have sort of sufficient number such that, I want to say like a complete basis or something like that.
Why is rho v?
Right.
Oh, okay, so rho v is unique because essentially you can actually solve this. So this is the expectation value of the operator in a given state, and this is a set of linear equations which you can then solve because you assume that you always pick a nice basis of operators here. You always pick operators which have inverses, so then you can solve this nicely. And I will always work implicitly or explicitly with operators with a basis. I can always choose a basis in which I can solve this nicely and express this rho v in terms of these basis elements with a well-defined coefficient. I didn't want to go into the details because it's not going to be relevant for what I'm going to talk about, but I can talk about this in detail later if you want to see it done. Did that answer everyone's question? Okay, good. Okay, so this uniquely gives me a reduced density matrix associated with an algebra. And then I can just take the standard von Neumann entropy of it and call that, that number, the entropy of the region V. Good. Now, this is a powerful definition, and it's a bit too powerful in some sense. You need to be careful what you're computing. One thing that you need to decide is what is the set of operators that is associated to a given region. This is there is no unique answer to this. There's no canonical way. Well, there's a natural way, but there's no God-given way to there's no unique way to associate to every region a single set of operators. You can remove one of your basis elements of the algebra, or rather one of the generators of the algebra, as I will discuss in a second, and you will still get a slightly smaller algebra, which is supported on V, but is not supported on any region smaller than V. This is possible. An example, you keep a position operator, but you remove a momentum operator for one of the sites. That's a standard example to keep in mind. So, and then you can do this for randomly chosen sites. So you can get many different algebras which are only supported on V and not on any smaller set. But then you need to decide which one of these is the one naturally associated to V, if there is one. And then not only that, but then I was being slightly coy about these traces here. I do not say which representations of the algebra they're taken in. Before I told you that this trace was a trace over the Hilbert space in the interior. Now I just didn't specify anything. And in fact, it turns out that both of these choices, both choosing the representation and choosing the algebra corresponding to a region, actually matter. Like, it's not like it gives you some change to a non-universal quantity. They actually affect universal quantities. And understanding this also, and in fact, understanding this also answers this question about mapping entanglement entropy under duality. Because it turns out that if you have a rule for assigning an algebra to a region, then dualizing the theory sort of changes this rule. Very schematically, and I will explain this in the rest of the talk, think of this rule as sort of imposing boundary conditions at the edge of your region B. Don't worry about the details, I will explain them. But think of the rule as assigning boundary conditions to your region. And essentially what duality does is it exchanges, let's say, Neumann with Dirichlet boundary conditions, which is extremely natural. And in fact, from BCFT studies, we know that duality does that already. This actually, the analogous thing actually happens with entanglement entropy. Good, and I will describe what I mean by boundary conditions in a second. That's the entire point of this talk. But anyway, the fact that these choices exist has made some authors, slightly pessimistic. This paper by Casino and Rothebal, which sort of introduced this algebraic method of thinking to the masses, also started speculating that maybe one should not even calculate entanglement entropy anymore, because you have all of these choices. They affect universal quantities, so maybe you don't know what you're doing anymore. And maybe you should just work with some kind of smoothed out quantities like mutual information or something even fancier, which are rigged in such a way that they are not sensitive to these choices of algebras. I'm a bit more optimistic than that. I will say that you can understand what each of these choices does, and you can actually start analyzing what each of them predicts for universal terms and start understanding which ones are the ones you normally talk about when you talk about, let's say, holographic entanglement entropy. Or when you talk about two-dimensional methods, CFT methods for calculating entanglement entropy. So this can be understood, and it's actually, you should just think of all of this as a vast generalization of the concept of entanglement entropy. That is also useful for fundamental reasons, because then you need to understand it in order to understand, let's say, dualities. It's also useful for other reasons that I will describe near the end of the talk. Good. Any questions?
What's an example of universal star algebra for unit interval?
Oh, that's a continuous question. So let me first regularize your question. So let's say I have a lattice with finitely many points on that interval, and I take a compact scalar, and I just pick up all the possible position and momentum operators at each site. Or an even simpler example, which I'm going to actually describe in greater detail, you pick the set of all Pauli matrices at each point. So you get a 2x2 matrix at each site. You have n sites. You look at their direct products. So you have an algebra whose dimension is d equal to 2 to the n. That's the Hilbert space of this. That's the Hilbert space of that region of a spin chain, and that is an algebra. It's closed under multiplication. It's nice. I will show you what boundary conditions mean in that case, etc. I don't want to talk about continuous operators on the real line. Okay, so the next order of business will precisely be to give you explicit examples, to stop sort of being kind of vague and abstract, and to actually give concrete examples. In particular, the examples concerning gauge theories are important because they still make physicists slightly uncomfortable. You know, people think that gauge invariance is ruined or something like that. So it's good to see that things work out and that you can think of them in a useful way. And then, as I said, essentially the way I want to, the main takeaway lesson will be that different choices of algebras can be nicely associated to different boundary conditions that you can put on the entangling region, on the edge of the entangling region. Because of course, as anyone who reads, if you read any paper essentially on entanglement entropy, you'll find that it's most commonly computed by doing this thing called the replica path integral, and basically introduce some conical singularity in your region, in your space-time, and you compute a path integral on this on this slightly singular space-time. And essentially choosing how to regulate this conical singularity corresponds to different, in the path integral corresponds to choosing different things here in this Hamiltonian framework. So I will give explicit examples of how that works. And then I will point out that there is a slightly more natural than other choices of algebra on a given region, which is the maximal one. So you take all the possible operators that are allowed in your region, and if you compute the entropy associated with that maximal algebra on a given region, in the theories where we can compute it, it always ends up matching the stuff that we expect. The universal terms match the trace anomalies. The expression matches the one that's obtained via holography. And so the conjecture will be that the stuff that you will see in 99% of the papers that have been calculating entanglement entropy is always the entropy of the maximal possible allowed physical algebra on your region. In the case of gauge theories, it will be the maximal possible gauge invariant algebra. So, good. And then finally, I will present I will remark on this interesting other thing, which is that in some theories it turns out that it's important to write the reduced density matrix as acting on the entire space of degrees of all possible degrees of freedom, gauge invariant and non-gauge invariant. And that, of course, it's still going to be a gauge invariant operator, but you need to write it as an operator which acts as the identity on all the gauge non-invariant degrees of freedom. And these factors of identity will actually give you extra entropy, which is needed to reproduce known results. So if you want to take a non-abelian transsimulus theory and reproduce its universal piece of the entanglement entropy, which is called the topological entanglement entropy, you will actually need to assume that the operator is defined not just on the space of gauge invariant degrees of freedom, but on the space of all possible degrees of freedom. As I said, it's still going to be gauge invariant, nothing will be ruined, but you need to add these multiplicities. This is like adding information on the dimension of your representation of the gauge group, which is needed to give you the numbers we expect from the continuum. This is related to this fact that you have to choose the representation wisely, that it matters which representation you choose. But this is going to be at the end. Okay. Good. Any questions? So let me give you some examples of algebras. Right now, I'm not even focusing on particular regions. I'm just giving you examples of algebras. And in particular, I will specify algebras by specifying their generators. So this is a set of operators whose all products give you the entire basis of your algebra. So an arbitrary element of an algebra is given by some linear combination of generators and their possible products. Okay, so in a fermionic system, and again, I'm going to talk about the discrete systems, and for now I'm going to talk about objects that are defined on sides of some discrete lattice. and all the sites will be called V. So for a fermionic system, the algebra is always very simple. You have two operators, you have two generators per each site. This is a spinless case, one flavor, the simplest possible fermionic theory. You have two operators per site. You can think of them as the fermionic raising and lowering operators. And all of their possible products, over all possible sites, generate your algebra. Similarly, a spin system also has a two-dimensional Hilbert space at each site. You just have two Pauli matrices, x and z, or sigma x and sigma z, at each site. Their products give you the identity and the third Pauli matrix on a given site. And so these guys at each site generate the entire algebra. And as we discussed a few minutes ago, there's going to be the entire Hilbert space. This entire space generated by, the algebra generated by these guys is actually going to be precisely the algebra of complex matrices whose dimension is 2 to the n, where n is the number of sites v. And then a slightly more complicated scenario is that of just pure compact scalars at one per site. So there you have a position operator at each site, and you have a momentum operator or a shift operator at each site, and then you can combine them in various ways as usual. Then of course you can just easily discretize this. So this here I wrote them as continuous operators, but I can easily discretize them and get what's called a clock model. So something which has k different positions and can be shifted by at most k sites until you get back to the beginning. I will not work with these discrete versions, but I'm just saying that this can be totally nicely regulated. So all of these kinds of operators, all of these kinds of generators will end up generating the maximal possible algebra on this specified number of sites that we have.
Are you saying these sets mutually
Here and here, yes. Here, no.
Okay. So I mean, are the size like are they 2 by 2 or?
Yeah, that's right. So
Okay.
yeah.
Okay,
So each of these are just the standard, 0, 1, 1, 0, and well, roughly, if you don't have any other sites, you can think of psi bar, psi dagger, and psi as this. Of course, you can't just think of them as just being direct product of two sizes, not this, because as I said, it has to be graded because they anti-commute. So there's some generalization of it, which takes into account that size of different sites commute. But yeah, roughly, you roughly think of each of them as contributing a 2 by 2 matrix. Good. And so these were generators of maximal algebras. But then important things happen when you look at non-maximal algebras too. In particular, two examples which are important are as follows. So you can look at the algebra that's generated just by fermion bilinears. So just by the bosonic subset of a fermionic algebra of operators. And the reason why this is nice is because this dualizes nicely to a bosonic system. This dualizes locally to a bosonic system in every dimension, actually. So that's why, and that will solve this problem of ordering ambiguities. So you can define an entropy associated to a fermionic system if you look at the non-maximal algebra that's just built out of bosonic operators. That's unambiguously defined. For some meaning of unambiguous, which I may discuss. More importantly, you can imagine having a gauge theory where instead of having degrees of freedom on sites, you have degrees of freedom on links, and then you don't allow every possible operator. You only care about a relatively small algebra of operators, that's generated just by the gauge invariant ones. So, but that is generated by essentially magnetic fields on lattices of your faces of your lattice, and by the electric field operators that shift your gauge fields on each link. So, yeah. So this is just a silly lattice convention. I tried to not put too many details on lattice nomenclature here. So every time I have sites on a lattice, they will be denoted V, like for vertex. Links will be denoted L, and they will always be assumed to be oriented, so I can always identify the beginning and end of a link. Faces will be denoted F. And then there are natural operators that act as boundary and co-boundary operators. So boundaries are standard geometrical boundaries, and the co-boundaries, just think of them as exterior derivatives. So I have some function that's defined on links. Delta A defines a function that's defined on faces, so it's like a two form, and it does precisely what you want it to do. It just calculates it just takes that kind of derivative. So this can be made precise, and I don't actually need to go into precision here, but everything is perfectly well defined.
Should we think of the convex scale as also defined? Or is it not?
No.
It's just derivative of respect.
Yeah, that's right. So this, so here the original degrees of freedom are all on links. Here they're all on sites, and this just shifts the degree of freedom on one site and doesn't touch any others. Okay, and the important thing about non-maximality of an algebra is that it has a center. For these fermions, the center is, there is a simple Z2 operator, an operator that squares to the identity, which commutes with every other operator. And this operator is essentially we often call -1 to the F, and people call it the Fermion parity. So the point is that no fermion bilinear will change the Fermion parity of your system. Similarly, if you only look at the gauge invariant algebra, then actually then you have a central operator at each site. And of course that's called the Gauss operator. It measures the amount of electric flux flowing in or out of that site. And the entire point is that no gauge invariant operator can change that. So the point about non-maximal algebras is that they have centers, and centers are interesting. Centers allow you much more control over your algebra than in case they're not present. And in particular, from now on, I will always assume that your starting state rho is an eigenstate of all of these central operators, meaning that you can always, meaning you have a definite charge at each point, meaning that the Gauss law is always obeyed at each point, or that you always have a state with a definite number of fermions. Good. So centers are, as I said, interesting. And in particular, when there is a center, that means because it computes with everything, that means you can diagonalize everything nicely. You can choose a basis in which every element of the algebra with the center is block diagonal. And these blocks are labeled by the eigenvalues of each central generator in the system. So in the fermionic case, you had a single generator, this -1 to the F. It only has two eigenvalues, plus and -1. So your Hilbert space really splits into a fermion odd and fermion even sector. That's it. And as I said, these things are fancily called superselection sectors. In a gauge theory, Hilbert space is obtained just by a product of all possible states on all possible links. Splits into many states. But normally what we call a gauge invariant state obeys Gauss's law. So each of these G's has eigenvalue 1. And so only one of these many sectors is actually populated. You want to think that my density matrix is just 0 in every other sector, and everything I need to know about the gauge invariant state is in just one block of this density matrix. So far everything I said had nothing to do with subregions or anything like that. Now, of course, this entire discussion applies to choosing specific subalgebras within a region. So every time I choose a non-maximal algebra in a region, my reduced density matrix will become more and more block diagonal. And in particular, if I only make choices that depend on whether I have generators at the edge of my entanglement region or not, let's do that for simplification. If I only vary that, if that's the only choice I make, then so then any possible central operators that exist in my algebra H will be supported only on the entangling edge, and therefore my reduced density matrix will be block diagonal with blocks labeled by eigenvalues of operators that live on the edge. Think of them as values of fields. Think of them as being states with definite values of certain fields at the edge. This is just boundary conditions. I'm just saying that picking an algebra, picking which central operators I have, picks the type of boundary conditions that need to be obeyed. It says that every state in a given sector has to be an eigenstate of a let's say a position operator on the edge. Okay, here are some examples. So spin chain on an interval. So originally you start with some number of sites on an interval, and you have two generators for each site. The reduced density matrix in this region, it has no constraints. It can be anything. And I call that open boundary conditions. There's no requirement that the density matrix be anything special. But now let me assume that I look at an algebra which is missing one generator. It's missing the Z generator here. Then the conjugate generator, X, is actually going to be central. It has to commute with everything else. There's nothing that fails to commute with it. And therefore, every state, so that's in the reduced density matrix appropriate to this algebra, will be an eigenstate of this X. And so I can think of the reduced density matrix as having only states with definite values of X on the edge. That's like fixing a boundary condition of some sort. Normal boundary conditions also work. They're a bit more interesting. So now instead of removing one operator, I remove two operators but keep their product, like so. And then you can convince yourself that the product of the other two operators, the product ZZ, now commutes with everything. Because this Z anti-commutes with this X, this Z anti-commutes with this X, together they commute with this guy. So therefore, the product of these two Z's is a central operator, and therefore the derivative in this direction is fixed in my reduced density matrix. And I can do fancier things. I can remove an operator of one sort from one end and an operator of another sort on the other end, and get various mixed boundary conditions. This all works. The entire point is that every time I remove some operators, I get a center, and that corresponds to having a particular choice of boundary conditions chosen. Good. Now, in the context of gauge theories, the maximal possible algebra that lives on a given region, the maximal possible algebra of gauge invariant operators on a given region, has a center. The center is generated by the electric fluxes leading through the region, essentially, by the products of all electric field operators that emanate from a given site on the boundary. This is called the electric center choice. And then people say that there are electric edge modes. Basically, your Hilbert space, your reduced density matrix will split into blocks labeled by configurations of outgoing electric flux. And as I talk about all of this, just keep in mind that I'm always talking about this full Hilbert space of a gauge theory, meaning that I always assume that every trace, everything is always taken in the representation where I just have a nice degree of freedom on each link. So that's my Hilbert space. I don't project into some gauge invariant sector of the Hilbert space. the gauge invariance all comes at the level of operators. Good. Now, for the discussion of boundary conditions for fermions is the same as the discussion for spin systems, because, as I said, they can be, the bilinears can be bosonized. And this actually works in every dimension, which is not obvious. You know, bosonization was easy in one plus one dimension. In higher dimensions, doing it exactly on a lattice was actually figured out like in the last 2 years. In a completely general case, it works on every lattice, etc., not in special cases. But it works, so the discussion is the same. And the crucial thing I want to emphasize, now going back to a scalar theory, is that when I say that a particular algebra corresponds to a particular type of boundary condition, I actually mean it corresponds to all possible boundary conditions of a given type. So you have to take into account, if you're talking about Dirichlet boundary conditions of a given field, you have to take into account all possible fixed configurations of the field, not just the field going to 0, which is what we normally call a Dirichlet boundary condition. When you say, oh, I set a particular field equal to 0 at the boundary, you actually need to say, I set a particular field equal to any possible constant on the boundary, and you need to sum over all the possible constants. These possible constants k are things that I can call the HET modes.
Would you make the same statement about boundary conditions?
Yeah, that's right. So all possible values of the derivative, yes. Yeah. If you don't do this, then you will not get the right universal terms, which is what people were confused about. This is this negative contact term of Cabot, which is also resolved by actually looking at all possible boundary conditions and not just imposing a particular like brick wall solution where the field just vanishes. Good. And as I said, so if you now start computing in free theories where we know which are conformal, so we know what kind of trace anomalies we expect from them, and we know how these trace anomalies are supposed to manifest themselves in the entanglement entropy, you start computing, and you see that in both gauge and scalar theories, you will always get that the standard conformal anomaly comes out of the entanglement entropy of a maximal algebra in a given region. These regions usually have to be spherical for these calculations, but okay, that's a technical point.
Can you define maximal now?
Sorry?
What is maximal?
Maximal, well, again, so you take a spherical region and you put, or something that's on a lattice and approximates a sphere, and then you put all possible operators on that, and you look at an algebra comprised of all possible operators on every site within that sphere, or on every link within that sphere. Good. And as I said, it's important to sum over all possible boundary conditions of a given type when you calculate this. And that brings me to this conjecture, which I stated already at the beginning, that it seems that every time we say that entanglement entropy computes interesting trace anomalies and detect and can serve as a definition of the C theorem in various dimensions and so on, we have always been computing it using the maximal algebra of the given theory in a given region. This has always been the case in all the calculations essentially done so far. This wasn't obvious that it was the case, but it was. And I'm going to motivate why the maximal algebra ends up giving you the nice central element, the nice trace anomalies in a second. I won't say prove, but motivate for sure. And to motivate this, let me first focus again on gauge theories. So far everything I said worked in any state. So I just said, oh, by choosing a particular algebra, I get particular block diagonal decompositions. But let's say I pick a special state in which some operators are effectively 0. Basically, any expectation value in that state that involves a particular operator ends up being 0. There are certainly states like that. And if I do that, then that's essentially like choosing a block diagonal density matrix from the beginning. So this sort of gives me effective operators, effective central operators, central in a given state. because all of the operators that compute with them have vanishing, that fail to compute with them have vanishing expectations in that state. So I could do something like that. I could certainly find states like this. In particular, if I pick a gauge invariant state, then I can pick any gauge variant operator. Let's say an open Wilson line, just e to the IA on some link. And of course, there's an old theorem saying that every gauge variant operator has to have vanishing expectation in a gauge invariant state. This is called Elitzer's theorem. And in particular, this means that gauge invariant states are such that we never had to specify that we were working with a gauge invariant algebra of observables. We could have just said, oh, we're working with all possible operators, gauge invariant or not. But because we've chosen our state to be gauge invariant, that was the same as working with just the gauge invariant ones, because they're the only ones who are allowed to have non-trivial expectations. So this takes some getting used to. So I will rewrite it like this. So basically, I'm going to say that instead of having electric boundary conditions, instead of thinking of having electric boundary conditions because you're working with a non-maximal algebra, you can just think that you're working with open boundary conditions, but in a particular state. And that state sort of says that, you know, constrains the possible configurations here. So I've transferred the burden of being block diagonal, of causing block diagonality, from the algebra just to a particular choice of state. This is important just for conceptual clarity, because before I go into the mathematical description, I'm going to say it's essentially going to end up saying that in every theory we know, the correct trace anomalies are obtained by working with the maximal possible gauge, the maximal possible algebra. But of course, you have to, with the only caveat that you should always choose a gauge invariant state if it's a gauge theory. So, so it's really the fact that there are all these open boundary conditions that somehow you're not putting in any extra impositions on your state through the algebra. That's allowing you to get the trace anomaly you expect. And that becomes even clearer in the path integral picture here. So let me backtrack. Let me remind you how replica path integrals work. So let's pick a superselection sector or some of an algebra. So this row VK is the density matrix in a single block. And that Hilbert space is spanned by some fields, which are generically called phi k. And the matrix elements of this within this block are given by a path integral of this sort. So I do a path integral over the entire Euclidean plane, but I put in weird boundary conditions at the tau equals to 0 slice. At just a single spatial slice, within my region, which is between these 2 points, I put in one boundary condition on one side of the region and another boundary condition on another side of the region. And at the edges, I just force my fields to be in whatever my center tells me that they have to be, like in a particular value of the edge mode k. So, and then I do the path integral over all configurations theta, or at this link, and all the configurations phi everywhere else that just satisfy these boundary conditions. And it turns out this gives me the right density matrix element. This is why computing these things is actually possible. And then if I want to calculate the entanglement entropy, instead of doing this trace row log row thing, I can instead do the following. I can compute trace row to the n, and then take the derivative with respect to n. Sort of analytically continuing the number of copies n, and formally write this. So here I have an path integral over this plane repeated n times with different, and with these boundary conditions differently moved to each other, but with this k is always the same. So I get this conical manifold, but with a particular set of boundary conditions chosen at this end of at the tip of the cone. And this is how I draw it, how I denote this. So this integral with k here just means that I'm working with particularly prescribed boundary conditions at the tip of the cone, and then I sum over all possible values for these boundary conditions. And the important thing is that when I work with open boundary conditions, then I'm essentially not limiting this sum. I'm essentially summing over all possible field configurations here as well. So open boundary conditions will always correspond to completely open boundary conditions in the path integral too. And when I'm working in a gauge theory, because I have integrals over gauge fields on temporal links, doing all these integrals enforces gauge constraints at each point. So it makes sure that the state I'm in is always gauge invariant. And because of that, my previous story holds. What I said, that instead of doing this and thinking about these cases having been fixed by working in a gauge invariant algebra, I could just say, well, even without knowing this, as long as I make sure I only sum over gauge invariant states at every point, the density matrix I computed this way would have automatically split into a block diagonal form. So basically, if you want to ask what path integral gives the right trace anomaly, it's always the one where you have where you have open boundary conditions. So you sum over all possible quantum degrees of freedom at the entangling edge, at the tip of the singularity. If you think about how you derive that entanglement entropy has to contain information on trace anomaly, this kind of becomes clear, because the way you derive this is you say that the trace anomaly is really contained in the expectation value of the one-point function of the stress energy tensor one-point function T mu. So, and you can express this function as just the derivative of the partition function with respect to the metric. So you just poke the metric a bit, like here and here, and that gives you that causes this one-point function to become non-trivial. And so having open boundary conditions means that the entire path integral only depends on this poking, and does not otherwise depend on what's happening at this entangling edge. You can get extra dependence on the shape of this entangling edge and so on if you put in extra constraints, if you put in some extra weighting, some extra edge modes. But then that will then change what you mean by, that will then change your derivation of the conformal anomaly. So that's morally why you get the right trace anomalies by always having open boundary conditions. But this was never proven in any kind of rigor. This was just, as I said, sort of phenomenologically discovered after the fact by computing different algebraic entropies. And finally, let me go back to this fact that I mentioned at the beginning, that it also depends, that the answers that I gave also depend on which dimension, on which representation I choose for my Hilbert space. So actually, everything I said so far does not depend on that, very crucially, because as far as I know, in all examples that are known, the dependence on this kind of on these choices of representations does not affect the universal term when you compute the trace anomalies. However, when you compute universal terms in an odd number of space-time dimensions, this actually matters. Recall that trace anomalies only exist in even numbers of space-time dimensions. So everything I said until now was really only justified in 1 plus 1, 3 plus 1, etc. dimensions. And technically, I didn't really tell you anything useful about 2 plus 1 dimensions, let's say.
Why?
Sorry?
How could I have seen that?
Oh, because I was essentially telling you, I'm talking about the choosing the maximal algebra, or singling out the maximal algebra as the one that gives you the right trace anomaly. Because there's no trace anomaly in 2 plus 1 dimension, I don't have any criteria to favor the maximal algebra there. That's what I meant. But of course, there are universal terms in topological theories in 2 plus 1 dimensions. And Chern-Simons is the main example where people have calculated these kinds of things. In particular, let's say if you're in an abelian Chern-Simons theory, so U1 level K, there's going to be a universal piece in your entanglement entropy that's exactly 1/2 log K with some minus sign in front. So this minus 1/2 log K is something that you want to understand where it comes from, if you can. Chern-Simons is not actually decisable, but there are ways around that. You can still use similar kinds of tricks to reduce Chern-Simons entanglement entropy calculation to the story that I described so far. And it turns out that if you want to get the right kind of the right kind of topological entanglement entropy for Chern-Simons in a non-abelian case, you actually have to take into account that these edge modes may give rise to non-trivial factors of the identity matrix in your reduced density matrix. That's essentially because, as you can see here, so the philosophy is as follows. So your superselection sectors in a non-abelian theory are labeled by all possible representations of your gauge group. So these things that I called K are now I can call R now. And it turns out that within each sector, with the prescribed representation, my reduced density matrix in that sector has to have this form. So it has to be this identity, tensor, some other stuff. That's in this full extended space or extended Hilbert space representation that I was talking about earlier. So, and so a lot of there was a fair amount of discussion on whether it's physical to look at these guys here. Essentially, these guys come here because we have lines of electric flux, which are essentially matrices. You have some color indices there that are contracted across the entanglement edge. So when you cut the entangling region away from the rest of the system, you start to split these guys and release some dangling color indices there. So your density matrix just knows that there's a dangling index there. It basically, and that index is actually contained here. So, and of course the identity matrix has non-trivial entropy in it. So each of these factors gives you a log DMAR entropy associated to it. And that's why these things affect your entanglement entropy. So you need to decide whether you want to keep them or not. And it turns out that for Chern-Simons theory, if you want to get the right answer, you have to keep them. So you really want to take all your underlying degrees of freedom seriously when you compute entanglement entropy. Even if you say that things are gauge invariant, that's fine. You can think of gauge invariant states. You can ask for entropys only of gauge invariant algebras. Nevertheless, you need to ask yourself how physical are the underlying degrees of freedom. Like I've given you other examples where I can just happen to take a nice, perfectly physical theory, like a scalar field theory, and just choose a slightly smaller algebra. And there we wouldn't have said that any of the underlying degrees of freedom are not physical. We would have just said, oh, I'm somehow, for some reason, in the current problem, blind to certain measurements. I cannot do some measurements. And that increases my entropy, essentially. These results indicate that it's natural to think about gauge theories in the same way. Not to try to always think about the gauge invariant Hilbert space, but for some fancy quantities, like entanglement entropy, you might want to think about the underlying degrees of freedom too. Even if, and as I said, everything I said so far is gauge invariant. In particular, these log Mark terms are completely gauge invariant. You might care, they only depend on the representations of the gauge group, which are not on any particular fancy combination of degrees of freedom that are not gauge invariant or anything like that. So nothing has been ruined. Everything is consistent. Everything can be done with enough firepower. Conceptually, I think a lot of the things are clear. And now the question is how to use this knowledge to understand more things. Most importantly, we know that the Ryu-Takayama formula exists. So we would like to ask, okay, so if we know how to what a gauge theory entanglement entropy is computing, what is its gravity dual computing? What can we say about the algebra of operators on the bulk side? So this is something that I won't say anything useful on right now, but I think that this kind of stuff connected to already existing work, like bulk modular Hamiltonians are equal to boundary modular Hamiltonians, etc. Like these kinds of things are probably the most precise tools we have for understanding operator reconstruction in the bulk. And then, of course, there's the other thing that one can ask, which is, I've just told you that aside from this one slightly more natural kind of choice of algebras, for every region I have many other choices of algebras, and they correspond to many other kinds of boundary conditions that are not open, but that are Dirichlet or Neumann or what have you. So we actually know nothing about those. We don't know what computes them in the bulk. For instance, understanding that would tell you a lot about which operators are precisely the duals of position operators in the bulk. So we don't know this. And it would be nice to understand this. In particular, it might also be true that the universal pieces of these other entropies obey nice C theorems as well. Just like we know that the original trace anomaly obeys nice C theorems, detects numbers of degrees of freedom, etc. So these are all questions that could be answered, hopefully, in the near future, now that we have this sort of nice point of view on these subjects. And with that, I'm going to stop and thank you for your attention and ask you for questions. Thanks. Yes.
The last point that you raised regarding the Radicevic surface.
Yeah.
Does that single out one of the entropies?
Yeah, because the Ryu-Takayama is essentially always designed to reproduce the trace anomaly. So it's essentially the same answer. In fact, when people study modifications of Ryu-Takayama, like higher derivative gravities, they define them to be whatever gives you the right trace anomaly. So yeah, but you can then start playing with different area functionals and see whether they will give you any of the other kinds of answers. I don't know what the other kinds of answers should even look like, but yeah, I mean, there's a chance people can do this.
Any other questions?
Other entropies, they are not all boundary conditions, those guys, or what are the other?
That they're not all open boundary conditions, but they're like possibly Dirichlet or Neumann, let's say.
Those are the other.
Yeah, or like completely random, yeah, completely arbitrary things.
I mean, so the one that you're talking about is the one that's sort of the most general, because it has all of them.
Right, I mean, yeah, that's right. Sort of the most,
That's the one you would expect.
yeah, as I said, the slightly most natural, yes, yeah.
I didn't understand, does it not matter which one of the models you pick, or you have 3 different models for those? Fermion analyze, compact boson analyze.
Yeah, or gauge theory.
Gauge theory analyze. So you're using all 3 of those at the same time, or you each one separately, do they all get the same answer? Or
Each one separately, each has different trace anomalies, and in each case the trace anomaly matches the one you get from the So each one is also a CFT in the right dimension. A free scalar is always a CFT. Maxwell, a free gauge theory is a CFT 4D, and so you know what their trace anomalies are, and then you can compute the entanglement entropy and check which algebra gives you that trace anomaly. So because you just essentially tune to the critical point on the lattice, and you expect that in the thermodynamic limit, in the large lattice limit, you will get the right answers, and that seems to be the case, yes.
In the interest of time, why don't we thank our speaker again, and then we can continue talking.
Does the pointer not work or something?
Oh, no, I just didn't compute.
Oh, okay.
That
It seemed like you were doing it, and then.
Well, no, I was sorry. I was actually just debating whether I should because I didn't want to destroy something else, and we're already late.
No, no.
Did you get any reply from Jane?
No, no.
It has to be modified.